Investing in railways companies in the 1800s, electricity ventures in 1900s, and internet startups in the early 2000s has produced more millionaires than any other economic activity across the whole human history. If you, like me, were too young to be at the party, don't desperate because a new generational opportunity is coming. Who believed Amazon was the future of shipping and logistics on Earth most likely believes the same for Redwire. The only difference is that logistics and infrastructure is just moving to space. Orbital Data Centers, or ODC, represented the next frontier of human civilization, and their implication goes far beyond technology. In fact, through AI, cognition is for the first time in the history of Homo sapiens outsourced to an artificial device. That never happened, and this is the first time in 300,000 years since sapiens' appearance on Earth. Space exploration parallels that by expanding human consciousness and capabilities. We are becoming a multiplanetary Kardashev species, and we need more and more energy. The Earth and what it contains is no longer enough to satisfy our energy-hungry data centers. So we turn to space. NVIDIA, Rocket Lab, SpaceX, and even Redwire are working right now as we speak to build the new space economy. While for ODCs there are already several interesting proof of concepts out there, the reality is that scalability remains a problem. We are going to see in this video what the problems are and how Redwire is solving them. As large language models, or LLMs, grow in complexity, they require more training and inference, which is associated to more compute, more time spent, and therefore more energy. In practical terms, that means large data centers and large power distribution and production facilities. And here is where the first challenge comes. To aliment a large ODC, you need more current and longer wirings for power transmission, as the size of the ODC scales up. Joule's law shows the relationship between the current I and resistance R and the power transmission losses. As you can see from the equation, an electricity increase by a factor of 3 produces 9 times more losses. Similarly, power losses grow twice as faster as the length of wires that transport the energy required to power the ODC. This is a classical problem of balancing trade-offs. Interestingly enough, 99.99% of the energy is dissipated in the form of heat. And this is something few are truly talking about today. There is a way to circumvent, though, the challenge by reducing the resistance, which depends on the thickness of cables transporting the energy. By increasing their diameters, you can get lower resistance and therefore minimize losses. As I said, this represents a mere trade-off, as by increasing cable size, we are also increasing mass and therefore we are increasing the cost. Another challenge is the radiator heat rejection, essentially generated by two sources, one internal and one external. Internally, we can see how the Stefan-Boltzmann equation expresses the relationship between environmental temperature and radiator heat. More compute would require, of course, a larger radiator area. That's because it needs to dissipate heat away. Once again, we have a trade-off problem here. The larger is the radiator and the more challenging it becomes to transport heat. That also increases the cost of production of the radiators themselves. But a part of trade-off is also the external source of heat. I mean, we also need to consider the external part. Namely the fact that direct sunlight in space will hit the radiator at 1361 watt per meter squared, making it less effective, is also part of the problem. In addition, the Earth emits infrared radiations. That is essentially the measure of how warm the Earth is after receiving the sun radiation. From its surface, Earth emits roughly about 390 watts per square meter from its surface. This heat contribution will need to be taken into account when it comes to designing the ODC's radiators. Finally, one part of the sun radiation gets absorbed by the Earth, increasing its temperature that will contribute to its later infrared emission, just like we just saw, while the remaining sun radiation gets reflected back. That radiation hits on the way the ODC, and its heat contribution cannot be ignored. Some other challenges, in fact, come from the actual physical geometry of the solar array that power the data centers. Larger ODCs will require more energy and therefore larger solar array wings. Euler-Bernoulli shows that this can become a problem. Stiffness of the panels increase at the power of 3 as wings length grows. That can easily cause signal delays and structural damages. But it's not just about managing the size in space, it's just about how to actually send them in space. With these sizes, it's becoming quite challenging to make them fit even in the largest rockets, such as, for example, SpaceX Falcon. So there is a clear problem of packaging here. Another important challenge has to do with electronics reliability, because those circuits are exposed to cosmic rays, to cosmic radiations, and therefore they can be damaged by that. Although this is a serious challenge, the technology to rationalize the issue already exists. It's mature and it has been validated across GEO, LEO, and VLEO. Reparation, maintenance, and cybersecurity, of course, also represent main challenges to be taken into account. Now, given these challenges, how Redwire is solving them? Redwire is solving the power generation challenge by deploying its rollout solar arrays, or so-called ROSA. The very same arrays are already flying on ISS, Gateway, and multiple satellites, and represents today an industry benchmark. They can deliver tens of kilowatts of energy per wing, and by adding several of them, you can basically power an ODC. Redwire can also leverage its heritage in space thermal management systems, heat pipes, and other components to offer to the market the best space radiators. Additionally, Redwire is also known for its unique payload packaging techniques, and it offers a leading expertise in engineering and designing of high-tech architectures. So all of this tells us that if today ODCs seem to be feasible from the engineering point of view, they do not seem so much feasible from the econometrics, especially if we think to scale up the architectures. On the long run, material breakthrough or research and development might create new paths for applications and therefore resolve the issues upstream. But in the meanwhile, I believe that Redwire can propose interesting solutions and architectures that can fix or rationalize the issue as we speak. Here is what Redwire suggests in its white paper. It's called tiled architecture. Instead of a monolithic large block, the ODC could be optimized for losses, areas, and even cost by assembling more smaller blocks, where each block is the complex of GPU, power system, or radiator. If orbital data centers will become a reality in the next couple of years, I believe that the space value chain will look like the following thing. You would have at the launch level Rocket Lab, SpaceX, and other competitors. You might have the infrastructure level, Redwire, Lunar, and other. For orbital platforms, you would still have SpaceX, and as for solar array and thermal management, Redwire, of course, power production Redwire. And on the application level, alongside the GPUs provided by NVIDIA, you would have AI companies fully deploying and delivering their services. Now, my Redwire thesis here is very simple. The space economy is accelerating. There is a lot of capital, a lot of eagerness, and a lot of funds coming from governments. It's now a matter of geopolitics, and defense is just not pure, genuine space race. It's not soft power, but it's actually hard form of geopolitical strength. Therefore, Redwire is there to build the infrastructure and is acting just like those companies in 1800s in building the railways in America, or in 1900s, for example, take Edison companies in building electricity. Well, Redwire is doing the exact same thing, but not on Earth, but rather in space. And I believe that the thesis is quite solid because there is very little competition for what Redwire is doing. Is vertically integrated and is trying to expand its business across geography with a strong presence in Europe, but at the same time also across different sectors, both in space tech and defense. Thank you so much for watching the video. I hope you enjoyed the content. Make sure to like and subscribe and follow me on X for the latest insights about Redwire, and on LinkedIn if you're interested on AI, the GCC investments, and what's happening in the UAE, Saudi, and Qatar.